All right, so we got to talk work energy theorem here a little bit. It's my understanding that it was a little confusing the day I was gone when you were trying to do some of the practice problems. I'm pretty sure this screen did get put up at some point during the lecture there. Did everyone get it copied down? Okay. So just want to run through the steps here, and then I just want to do a ton of examples today to kind of illustrate how work energy theorem works. Okay, so quick review. Work energy theorem tells us that if work is done, so if a force is exerted through a distance, we are going to change the mechanical energy of either an object or a system. Okay, so an object would be I like directly push on something and make it move. That would just be me pushing on the object. Okay, a system could be like a bow and arrow. All right, I do work on the bow, but it's the arrow that ends up going somewhere in the end. Okay, that would still be me doing work on a system, and then the system conserving that energy and sending it out to other places afterwards. Okay, everyone kind of with me on that? Okay, so what we're going to be looking at today is when I read a problem, how can I determine what kind of energy is being changed by the work? Okay, so what are the two kinds of energy that we're most concerned with?
Potential and kinetic.
Potential and kinetic. Okay, and when we say potential, we specify gravitational potential energy. We've talked about elastic, but we don't actually do any calculating of elastic potential energy until we get to physics 20. Okay, so we're only going to be concerned with mgh for gravitational potential energy, or 1/2 mv squared for kinetic. Okay, so when you have a work energy theorem problem, the first thing you do is write out your givens. Okay, the givens you're going to get: force, distance, okay, mass, velocity or speed, okay, depending on if it's a kinetic energy problem, okay, or height if it's a potential energy problem. Okay, those are going to be your givens. Okay, then you're going to set up work is a change in energy, and we know that we calculate that with force times distance. Okay, at this point in reading the question, you have to decide, is the work being done changing the kinetic energy, or is it changing the potential energy? How will you be able to tell? If a question is talking about a change in potential energy, what's the object going to do?
It's like going to move further off the ground.
Right, it's going to move vertically.
Yeah.
Okay, probably upwards. Okay, but it's definitely going to move vertically, and there won't be any mention of a change in speed. Okay, because if we change the speed, we're changing the kinetic energy. That's how you identify. Okay, you just say it's force times distance, and either it's going to equal the change in kinetic, there's a speed change, or it's a change in potential, it's a height change. Okay, why in Science 10 they make it so that we can only do potential or kinetic, I'll never understand, because as soon as you get to physics 20, every problem involves a change in both. Okay, which means you never have to tell which kind is changing, because they're both changing, which I think makes it easier, but whatever. Okay, I don't make the rules, I'm just a peon. Okay, so what we have to do is decide what's changing, and then set it up so that force times distance, our work, is going to equal the change in whatever kind of energy we have. So if gravitational potential energy was changing, we would set it up so that we would have work, force times distance, equals our final potential, mg times the final height, minus the initial, mg times the initial height. Okay? And then we would just manipulate and solve for whatever the question wanted. If there's a change in speed, then we go force times distance equals the change in kinetic energy. So that would be 1/2 times the mass times this final speed squared, okay, minus 1/2 times the mass times the initial speed squared. Okay? Sometimes you luck out and one of these is 0. Okay, then you don't have to worry about the adding and subtracting. Okay, then final step, manipulate and solve. Okay, after that, and that's probably the trickiest part. It's just algebra. It's just moving things around. Okay. All right. Questions on the steps? Okay, as I go through these examples, you're gonna find me talking about each and every one of these steps. I talk about them every single time I do a problem. Okay, and I've been doing these for a very long time, but I still talk about each and every step. Okay, so I don't think you guys got to these ones the other day. Did you do the rocket? Okay. I want you to write this question down. I'll give you a minute to write it down, and then we're gonna walk through the steps. Okay, every once in a while, you luck out and you get a question like this. That's actually a lot easier than using all the steps I just showed you. And the reason for that is you don't need all the steps for this question. Okay? What are my givens here? What's the 200 grams? Mass. But it needs to be in? Okay, so I need the mass in kilograms. Okay, so 200 grams is how many kilograms? 0.2 kilograms, right? There's 1,000 grams in a kilogram. Okay, it's launched from ground level. What did they tell me there? My initial height is 0, yeah. Okay, and reaches a height of 1,600 meters. So that would be my final height, yeah. Okay, how much work is done? Well, they didn't tell me force or distance. Can I still do this? Yes. Okay, remember, we start out every work energy theorem question like this. Work is a change in energy. I'm not always going to need force and distance. Sometimes I can just use the change in energy. Is there a change in energy going on? What kind? Potential, yeah. Okay, so I can just go like this. I don't have to put the force times distance in because I don't know what the force was. Okay, I actually know what the distance was. What was the distance? 1,600 meters. But I mean, we're not going to kind of go there, okay, until part B. All right, so work is the change in energy. So I'm going to have the final potential energy minus the initial potential energy, because we already determined it's potential energy that's changing in this question. What is my initial potential energy?
0.
Right, because I'm on the ground. The rocket can't fall any further. It's already there. So subtracting 0 doesn't do anything mathematically, does it?
No.
All right, then we can just get rid of that. Sometimes we luck out that way. So would the work done on the rocket be equal to its final potential energy?
Yes.
Absolutely it would. Work's a change in energy, so okay, if I find the final potential energy and start it out with none, I'm done. All right, so m times g times h. Okay? All right, so I just need to plug in my numbers in. 0.2 kilograms times 9.81 meters per second squared, because I wasn't told it was anything else. Okay? Times the height, 1,600 meters. Sorry guys, I forgot to fire up the calculator here. Gonna let the hamster warm up. Okay, so 0.2 times 9.81 times 1,600. All right, so the amount of work done to get the rocket to 1,600 meters is 3,139.2 joules. Okay, that wasn't a terribly challenging mathematically question, was it? But it was contextually tricky. Okay? All right, now part B wants to know how much force the engine exerts. Okay, well, I got to go back to the beginning now. I know that this number is the change in energy, and it's also the work. So would force times distance equal that number?
Yes.
Yes. Since we just established that the work is done over 1,600 meters, can I find the force?
Yes.
Yes. Sometimes in a potential energy question, the height and the distance are the same number. Sometimes, not every time. Okay? In this case, they're the same number. If it was a bow and arrow being shot up in the air, then they wouldn't be, because this is directed to an object, whereas the bow and arrow would be a system. Okay, so it works differently there. The bow would only be drawn back maybe a meter, okay, where this is over 1,600. All right, so if I divide both sides by d, okay, which is going to be 1,600 meters, that'll tell me the force that was required. All right, 1.962 newtons. Is that very much force?
No.
It's not. Okay. Okay, does that make some sense? Okay. We still had to do both things, the force times distance. We just didn't have to do them together. They were kind of separated in that question. Okay, so here's one where the work is being done on a system. Okay, so let's have you write that one down and we'll walk through it together. Then I'll have you try a couple. So if I'm visualizing this, I got a rubber band and it's shooting a marble along a level floor. Okay, so we've just put something on the floor, okay, and we're pulling that marble back inside the rubber band and then we're just letting it go. What is the height going to change for this? No, it's just going to go faster. Yeah, it's going to increase. When it's in the rubber band and I'm holding it back, its initial speed would be zero. All the energy at that point is potential elastic in the rubber band. Okay, when the ball doesn't have anything yet. All right. So right off the bat then, just from the context of the question, we can establish that the kinetic energy of the ball is the thing that's going to change. All right. Writing down our givens, okay, 0.135 kilograms would be our mass. Okay, the rubber band is stretched using 300 newtons force. Okay, the marble starts from rest, VI, okay, and reaches a speed of 18 meters per second. All right, how far was the rubber band stretched? What am I looking for? Distance, yeah. Okay, so work is to change in kinetic energy. I have force, I'm looking for distance, so I'm going to have to do that part. And that's going to equal the final kinetic energy minus the initial kinetic energy, but this question cut me a break. What's my initial kinetic energy? Zero. Okay, so I can get rid of that. So what this comes down to then is force times distance equals 1/2 times the mass times the final speed squared, because the work is going to change the kinetic energy of the ball. Everybody all right with my reasoning so far? Mm-hmm. Okay, so I'm trying to find D. How do I get D by itself? Divide by F, right. I'm going to leave D over where it is and move F over to the other side. Okay, so now I'm solving for D. All I have to do is plug in my numbers. All right, 1/2 times 0.135 kilograms times 18 squared divided by 300 newtons. Okay, so the rubber band was brought back 0.073. Actually, if we were only doing two decimal places here, we'd say 0.07 meters. So 7 centimeters. Okay, that's how far it was drawn back. Okay, again, is that challenging algebra? It's not. What's challenging always about these questions is interpreting the story being told to get what you need. Emma, question that you had.
I'm just wondering about the math, because when I do it on my calculator, I get a different answer.
Are you doing it in 2 steps?
Maybe, is that what?
It probably is. If you put it all in 1 step, like if you look the way I did it, I did the top, and then I divided that by the bottom. If you put it all in 1 string, it divides 18 squared by 300, right?
So are you supposed to put it in 1 step, or?
No, I say you should do it in 2 steps.
But I think I did it in 2 steps.
Okay, let me come have a look.
Yeah.
Okay, questions on that one? Okay, these guys, the thing you gotta realize about these kind of questions is they're very, very patterned. Okay, it's always gonna be the same steps. Maybe not always in exactly the same order, but it's always the same steps. Okay? All right. This one's got a little extra algebra in it. It's not any different than the one we did on kinetic energy before, other than you have a little extra algebra. Okay, and I spoiled what kind of energy it was. Okay, give this one a try. Write it down and give it a try, and then we'll do it together. So I've got a 75 kilogram sprinter. So right off the bat, they told me the mass. Okay, and they can exert 225 newtons worth of force. Okay, so they told me the force. Over the last 10 meters of the race, that would represent my distance. They increase their speed from 14 meters per second to their maximum speed. So that would make 14 their VI. Okay, it's their initial. Okay, and we're looking for VF. Okay, all right, so obviously it's the kinetic energy that's changing here. So work equals the change in kinetic energy. And then since I have both force and distance, I'm going to put that formula in for work. And then on this side, I'm going to have EK final minus EK initial. Everyone okay with what I've done so far? Have we done anything different than the steps?
No.
Okay. What I'm looking for is VF. Would that be part of EK final or EK initial? All right. Is it easier to isolate that now before I put the formulas in? Can you do it after? Absolutely, in exactly the same way. But sometimes people are a bit intimidated about moving a whole bunch of letters algebraically all at once. Okay, so what I often do is I do it here. I know what I'm looking for is in this term. So before I put all the variables that are part of that term in, I move stuff around to isolate it. So how would I get EK final by itself? Add EK initial. All right, so I'm going to have the work or the change in energy plus the initial energy equals the final energy. Okay, if I talk that through in my head, that makes sense. If I take how much I changed the energy by and add that to what I started with, it should give me my final. That makes sense. Okay, can I put in my formulas now? Absolutely. Okay, so now I'm going to go force times distance plus 1/2 times mass times initial speed squared equals 1/2 times mass times final squared. Okay? Everybody all right with that? Okay. When I was at this step here, okay, would I also be saying this? Force times distance equals 1/2 mvf squared minus 1/2 mvi squared. Would that be true? Can I subtract 1/2 mvi squared all together over to the other side? I can. It's exactly the same as what you do in the acceleration formula when you add t times a or you subtract t times a. You would have to figure out what 1/2 mv squared is before you subtracted it from 1/2 mvf. So it's just a number. You can move it all together. Whichever way you're more comfortable with. Okay? This is the way I do it. Okay? Down here. All right. I'm trying to get VF by itself. So what do I have to do to get VF by itself now? Exactly. I've got to move the half and the m. Since they're all being multiplied, I just have to divide them over to the other side. Okay, that gets me VF squared. I just want VF. So what do I have to do? Square root. All right, I've isolated what I'm looking for. I'm ready to plug my numbers in now. All right, so VF is going to be the square root of force, 225 newtons, times distance, 10 meters, okay, plus 1/2 times the mass, 75 kilograms, times the initial speed, which was 14 meters per second. That's all going to be squared, and then I'm going to divide that by 1/2 times 75. All right, this is where you've really got to be careful with your calculator. Okay, your calculator is always going to want to do the things it was programmed to do, order of operations. Okay, in this case, we don't want your calculator to be in charge. You need to be in charge. Okay, so when I'm punching this into my calculator, I'm either doing it one piece at a time, or I'm putting in a ton of brackets to make sure it does things in the right order. Whichever way you're more comfortable with. For me, I'm more about, let's do it one step at a time. 225 times 10. All right, I got my work. It's 2,250 joules. I'm going to add to that the initial kinetic energy, 0.5 times 75 times 14 squared. Okay, that's the top, 9,600 joules. Okay, in fact, that is my final kinetic energy, 9,600 joules. If I divide that now by 1/2 times 75, okay, that I'll want to put in brackets, I get 256 meters squared per second squared. What do I have to do with this number? Square root it. That's VF squared. Okay. All right. So their final speed is 16 meters per second. So you know, they will never get more complicated algebraically than that one.
How do you know, like, square root it?
Because VF is squared in the formula, and I need to solve for VF. So I square root it so that I can get rid of the squared. Okay, questions on that one? Sorry.
I solved for work before. Is that fine if I just use W instead of FD?
Absolutely. Yeah, it's totally the same thing.
How many marks would that be out of?
That would be 5, maybe 6. Depends on how many steps I want to give you marks for. Okay, and I always try to give you marks for every step. Okay, so always make sure you show your work. All right, so there you go. That's the hardest one you could that I could give you involving kinetic energy. All right, write that one down and give it a try. So imagine you're lying on your back on the ground and you're pulling back a slingshot. Okay, that's what's going on here. All right, and I say that because I want you to understand that this is being fired from the ground. Anytime they tell you that, what's your initial height?
0.
Right, okay. All right, so on this one here, we're looking for the height an arrow will reach. If we're looking for the height, it's probably it's potential energy, but it's also which height, initial or final? Probably final, yeah. Okay, so final height is our question mark. Okay, it's fired straight up in the air from the ground. So our initial height is 0 meters using 300 newtons worth of force. Okay, while being pulled back 0.75 meters. All right, so there's our givens. And as we just said, because we see height changing here, we know that the work being done on the slingshot is eventually going to be gravitational potential energy for the rock, or sorry, arrow. Okay, everyone with me there? All right, so I have force and distance, so I'm going to put those into the formula. And I know it's potential energy, so I'm going to say EP final minus EP initial. What's my EP initial? It's 0. All right, so did me a favor there. I don't have to worry about any algebra like the last question had. Okay, force times distance equals mass times gravity times height final. I want to find height final. What do I do with M and G? Divide them over to the other side. All right, so all I have to do now is plug in my numbers. Final height is going to be 300 newtons times 0.75 meters divided by 0.09, I forgot to write the mass, okay, times 9.81. I forgot to put mass. All right, so when I plug those numbers in, 300 times 0.75, so there's the work or the final potential energy, right? Divide that by m times g, 0.09 times 9.81. All right, so that's going to get to a height of 254.84 meters. Okay, everybody all right with that? Okay. Should you hang around for that arrow to come back?
Probably not.
Probably not. I mean, in the real world, the arrow is going to tumble when it comes back down, so it isn't going to go as fast as you shot it. But in the perfect physical world, it would come back exactly as fast as you shot it. That would be bad. Okay? They actually had in the physics diploma exam a couple of years ago a question about the statistics of innocent bystanders killed by bullets that were not fired at them. They were fired straight up in the air. So people were, going, yee-haw, like, and just firing their guns up in the air. And the bullets were actually falling in other places and they were killing people. Okay? This is like conservation of energy stuff that we're going to talk about this week. When the bullet leaves the gun, it has a certain amount of mechanical energy. And that number doesn't change very much when it goes up in the air and comes back down. There's a little bit of, loss to friction, but it's still kind of deadly. So you should really not recklessly fire firearms because they're dangerous.
Even more.
It's really, really important to know that they're dangerous and they need to be treated with respect. They shouldn't be a glorified firecracker. They have a firecracker for that.
Yeah, why they use blanks at starting pistols.
Yes, yeah. But even like some on what was the movie Alec Baldwin was on, like that the director of photography or whatever it was that was killed, right? That was a blank, but there was a plug, and the plug was actually discharged, and it moved with enough force that it killed her. So even blanks, like you have to be sure it's an actual blank and not a plug. Okay, because a plug can still be dangerous. It's just not an aerodynamic bullet. It's just a chunk of metal, okay? But it's still dangerous. Okay. All right. But yes, that is why starter pistols use blanks. Yeah, definitely. All right. See if you can do that one. That one's pretty straightforward, I think. It's actually algebraically quite a bit easier than the one you just did. Okay, so algebraically speaking, this one's pretty straightforward because you don't have to do a lot of moving of things around, right? They tell us right off the bat that there's 60,000 joules of work done. Okay, that's a big given, right? In that you don't have to go and calculate it yourself. All right, so we got 60,000 joules of work being done. We know the mass of the elevator, 500 kilograms. Okay, from a height of 14 meters. Okay, to the top of a building. So this is HI, we're looking for HF. Everybody all right with that? Okay, so if it's change in height, what kind of energy are we changing? Potential. All right, so work is a change in potential energy. Okay, that's going to mean that work equals M times G times H final minus M times G times H initial. Or I could have also written it like this. EPF minus EP initial. All right? What I'm looking for is part of EPF. All right, so what do I need to do with EP initial? Add it to the other side. So that's either as EP initial and bring it over, or as MGHI. Doesn't matter which way. Okay? Work plus M times G times H initial equals M times G times H final. Okay? In my head, the change in energy plus the initial potential energy should give me the final potential energy. All right, I'm looking for HF. What do I have to do with M and G? Divide it over to the other side. All right, HF is by itself. Now I just have to plug in my numbers. 60,000 joules minus 500 times 9.81 times 14. Okay, there's my initial potential energy, and I'm dividing that all by 500 times 9.81. Whoop, I put minus, it's supposed to be plus. I don't know why I put a minus in there. Okay, plus 500. So plus 500 times 9.81 times 14. Okay, and then divide that by m times g, 500 times 9.81. All right, so the top of the building is 26.23 meters. All right, questions on that one? Is this making a little more sense than the other day?
Mhm.
Okay, I mean, when it comes right down to it, have I done basically the same thing on every question until the manipulation part?
Yes.
Yeah. Okay. Do a kinetic one. Okay, here's a kinetic one. We'll go back to the ramp. The ramp is a good question, but we've done like 3 potential in a row here. So, okay, give this one a try, and then we'll do it together here in a minute. So, question starts out talking about a bobsled team exerting a force of 800 newtons. So they just gave me force, 800 newtons. Okay, so then I kind of want to start picturing in my mind the context of the question. I'm picturing, you know, a four-person bobsled team, the sled's being pushed along, okay, and they're going to run 15 meters while they're pushing it. So I have force and I have distance. The bobsled is going to accelerate from rest. What do they give me there? Initial speed, right? Not that it makes a huge difference. Initial speed, which also tells me my initial kinetic energy. What's my initial kinetic energy? 0. Okay. And it's going to reach a speed of 9.5 meters per second. All right. So obviously it's the kinetic energy that is being changed by the work done by the bobsledders in this question. So work is going to be the change in kinetic energy. They told me force and distance, so I'm going to put those in right away for work, and I'm going to say kinetic energy final minus kinetic energy initial, which we already established is 0. All right, so this one's nice because I don't have a whole lot of things to move around. I'm just looking for mass in this one. All right, so I've got to expand out and put in the formula for kinetic energy. I'm going to have force times distance is 1/2 times the mass times the final speed squared of the bobsled. I want to get mass by itself. What do we do with the half and the v squared? Just divide them over to the other side. They're all being multiplied right now. The opposite of multiply is divide. Okay, so divide 1/2, divide v squared. They both come over here. Right, my algebra is done. I've just got to plug in my numbers now. So that's going to be 800 newtons times 15 meters divided by 1/2 times 9.5 squared. Okay, the thing most people would forget on this part is forgetting to square the 9.5 when they punch this into their calculator. All right, 800 times 15. So there's the work done by the bobsledders, 12,000 joules worth of work. So the kinetic energy of the bobsled is going to change, and that is the final kinetic energy of the bobsled. If I divide that by 1/2 times 9.5 squared, that'll give me the mass of the bobsled. All right, so the mass of the bobsled is 265.93 kilograms. I would assume that that means there are at least 2 people in it, because the bobsled is probably not that heavy on its own.
Okay, so I totally screwed up with this question. I somehow ended up with the same answer.
Well, that means you didn't screw it up that bad. You might think you did, but if you got the right answer, you couldn't have screwed it up that bad. Or you're incredibly lucky. If you were old enough, I tell you, go buy a lottery ticket, but you're not. Okay, so let's see what happens. Okay, so the trick with this question is determining which of those 2 numbers, the 22 or the 8.2, is the distance, and which one is the height, which one's the height?
8.2.
8.2. All right, so that's the trick. Okay, our final height is gonna be 8.2 meters. Our initial height is 0 when you're at the bottom of the ramp. Okay, the distance over which the work is done is the 22 meters. We're looking for the force here. Okay, so that's gonna mean the work is changing the potential energy, right? Force times distance is gonna equal m times g times hf minus 0. Our initial potential energy is the bottom of the ramp. Right, so all we have to do then is isolate force by dividing both sides by d. Right, so that's going to be 1.75? 1.2. Okay, 1.2 times 9.81 times 8.2 meters. Divide that by 22 meters. Okay, and you've got the force required. So 9.81 times 8.2 divided by 22. All right, so you're going to need 4.39 newtons worth of force. Okay. It's not that much. It's not a very big ball either. Everyone with me on that?
Yeah.
Okay, we'll work on a few more of those tomorrow, and then we're probably going to move on to law of conservation of energy. Okay? All right, good job today, guys.
Thank you.